The concept of nothing has puzzled and intrigued thinkers for centuries. Philosophers and scientists alike have grappled with the notion of a void, a space where nothing exists. This idea seems simple, yet it becomes profoundly complex when we attempt to define it. What does it mean for there to be nothing? Is there such a state where absolutely nothing exists? Or does nothing have its own subtle existence, a kind of background from which something might emerge? Along with this, it is often said that the universe started from nothing, but then the biggest question emerges: where did nothing come from? In order to answer these questions, we first need to go back to ancient times. You see, in ancient times, the Greek philosopher Aristotle approached the idea of nothingness with caution. Aristotle believed that nature abhors a vacuum, a notion often summarized by the phrase horror vacui. He argued that a complete void could not exist because, without anything to contain or define it, the concept itself would be meaningless. To Aristotle, space was always filled with some form of substance, even if it was not immediately apparent. He viewed the idea of absolute emptiness as not just impossible, but incoherent. This perspective dominated Western thought for many centuries, shaping how people understood the nature of existence and the fabric of the universe. As time passed and scientific inquiry advanced, the question of what nothing could be took on new dimensions. In the 20th century, with the rise of modern physics, the concept of empty space, or vacuum, became a hotly debated topic. Physicists like Paul Dirac, who contributed significantly to the field of quantum mechanics, started to explore the idea that even a vacuum, the seemingly empty space, was far from being truly nothing. Dirac proposed that a vacuum might actually be filled with particles and antiparticles that pop in and out of existence, a notion that suggested even empty space as a kind of structure, an underlying activity that defies the traditional idea of a void. This idea radically shifted the understanding of nothingness. In modern physics, a vacuum is not an absolute absence of matter or energy, but rather a space where particles might be momentarily absent, or where quantum fluctuations are constantly occurring. The vacuum, in this sense, is a seething background of potential, a place where particles and antiparticles can spontaneously appear and annihilate each other, creating an environment that is far from empty. This redefinition of nothingness plays a crucial role in our understanding of how the universe could arise from such a state. Against this backdrop, the Big Bang Theory emerges as our best explanation for the origin of the universe. In the early 20th century, scientists began to gather evidence that the universe was not static, but rather expanding. This revelation set the stage for one of the most profound shifts in our understanding of the cosmos. The Big Bang Theory was first proposed by Belgian physicist Georges Lemaitre in 1927. Lemaitre, who was both a scientist and a Catholic priest, suggested that the universe began from a single, incredibly dense point, which he referred to as a prime-val atom or cosmic egg. According to Lemaitre, this point contained all the matter and energy of the universe, and it began to expand and cool, eventually leading to the formation of galaxies, stars, and planets. 2 years later, in 1929, astronomer Edwin Hubble made a groundbreaking discovery that provided key evidence for Lemaitre's theory. Hubble observed that distant galaxies were moving away from us, and the farther they were, the faster they seemed to be receding. This observation implied that the universe was expanding. If the galaxies were moving apart now, then at some point in the past, they must have been much closer together. Hubble's work gave substantial support to the idea that the universe had a beginning, a moment when it emerged from an incredibly hot and dense state. The Big Bang Theory fundamentally altered our understanding of the universe's origins. Instead of being eternal and unchanging, as many had previously thought, the universe was now seen as dynamic, evolving over time from a specific starting point. This theory also raised profound questions about what existed before the Big Bang, or whether such a concept as before even makes sense when discussing the beginning of time and space itself. What makes the Big Bang Theory particularly compelling is how it connects to the concept of nothingness. If the universe started from a singular point, a point where the density of matter and energy was infinitely high, then what existed before this event? Here, the philosophical and scientific definitions of nothingness intersect once again. Some theories suggest that the universe could have emerged from a quantum vacuum, a state where nothing in the traditional sense still contains a potential for creation due to the inherent fluctuations predicted by quantum mechanics. In this context, nothing is not truly empty, but is instead a fertile ground from which the universe could spring into existence. The very fabric of space and time might have been born from these quantum fluctuations, a process that aligns with both the philosophical musings of ancient thinkers and the modern scientific understanding of the vacuum. Thus, the question of how our universe started from nothing is intertwined with our evolving understanding of what nothing really means. The Big Bang Theory, supported by the discovery of the expanding universe, provides a framework within which we can explore this mystery. It suggests that the universe we know, with all its galaxies, stars, and planets, began from a state that might seem like nothing to us, a state without form, matter, or structure, but one that was rich with the potential for everything to emerge. This concept of the universe emerging from nothing leads us to one of the most fascinating aspects of modern physics: quantum fluctuations. These are tiny, random changes in energy that occur even in the vacuum of space. Though seemingly insignificant, they may hold the key to understanding how something can arise from nothing. The idea of quantum fluctuations was first supported by experimental evidence in 1947, when Dutch physicists Hendrik Casimir and Dirk Polder conducted a groundbreaking experiment. They discovered what is now called the Casimir effect, which showed that two uncharged parallel metal plates placed very close together in a vacuum experience an attractive force between them. This force wasn't due to conventional electromagnetic interactions, but instead resulted from the quantum fluctuations in the vacuum between the plates. This phenomenon demonstrated that what we traditionally consider as nothing is not truly empty. Instead, the vacuum is a seething background of activity governed by the uncertainty principle, a cornerstone of quantum mechanics introduced by Werner Heisenberg. This principle states that it is impossible to know both the exact position and the exact momentum of a particle simultaneously. As a result, particles and their corresponding fields can never be completely still or absent, even in a vacuum. In the quantum vacuum, particles constantly appear and disappear, creating these fleeting fluctuations of energy. While these virtual particles don't exist in the usual sense, they don't persist long enough to form stable matter. They have real, measurable effects, as seen in the Casimir effect. What does this mean for the origins of the universe? The idea that quantum fluctuations can give rise to something from nothing is central to quantum field theory, which describes a vacuum as a dynamic state filled with potential energy. Under the right conditions, these fluctuations could trigger significant events. In the early universe, just after the Big Bang, the conditions were incredibly extreme, characterized by unimaginably high energy levels and rapid changes in temperature and density. In this environment, quantum fluctuations could have played a crucial role in shaping the cosmos. This brings us to the theory of cosmic inflation, proposed by physicist Alan Guth in 1980. According to this theory, the universe underwent an unimaginably rapid and exponential expansion just fractions of a second after the Big Bang. During this period, quantum fluctuations were stretched across vast distances, imprinting tiny variations in the density of the universe. Although these fluctuations were incredibly small, they acted as seeds for the formation of galaxies, stars, and other large-scale structures. Gravity later amplified these tiny irregularities, leading to the richly structured cosmos we observe today. In this way, quantum fluctuations not only provide a mechanism for how the universe transitioned from a nearly uniform state to its current complexity, but also hint at a profound idea. The universe itself might have arisen from a quantum fluctuation. Some theories suggest that within the quantum vacuum, a fluctuation could have set off the chain of events leading to the Big Bang. In this view, the universe did not require a pre-existing state of something to come into being. Instead, it could have emerged from nothing, or more precisely, from the quantum vacuum, a state far from empty. This concept challenges our classical notions of cause and effect, creation, and existence. It suggests that the universe doesn't need a cause in the traditional sense because the quantum vacuum operates under laws where spontaneous creation is not only possible but inevitable. However, this idea is still the subject of much debate and research. While quantum field theory provides a framework for understanding how the universe could arise from nothing, many details remain unresolved. The exact mechanisms by which such a fluctuation could lead to the universe we observe today are incredibly complex and not yet fully understood. Nevertheless, the notion that our universe might have emerged from a quantum fluctuation offers a tantalizing glimpse into the profound and often perplexing nature of reality. It suggests that what we perceive as nothing is, in fact, a fertile ground of possibilities where the seeds of something, and indeed everything, are always present, just waiting for the right conditions to take root. In this sense, the story of our universe's origins is not just about a single moment in time but an ongoing dance of creation and destruction taking place in the quantum vacuum. It's a story where the boundaries between nothing and something blur, and the tiniest fluctuations can lead to the birth of stars, galaxies, and entire universes. As we explore these profound ideas, we find ourselves continually returning to the age-old question, how can something come from nothing? Quantum mechanics, with its strange and counterintuitive principles, offers one possible answer. It reveals a universe where even the emptiest spaces are alive with potential, a reality where the seeds of creation are ever present. The story of our universe is not just a tale of beginnings, but of continuous evolution, where the interplay of forces at the quantum level shapes the vast cosmic structures we see today. From the tiniest fluctuations to the grandest galaxies, the universe reminds us of the astonishing complexity hidden within what might seem like nothing at all. Would you like me to expand further or refine any specific sections? The early universe and cosmic inflation. Rapid expansion of space would have effectively flattened out any curvature, much like how the surface of a balloon appears flatter as it is blown up. This means that, even if the universe had started with some curvature, inflation would have stretched it so much that any deviation from flatness would become virtually undetectable, giving us the flat universe we observe today. Inflation theory didn't just solve these two problems. It also made several predictions that have since been confirmed by observations. For instance, inflation predicts that the universe should have slight fluctuations in density, leading to the formation of galaxies and large-scale structures. These fluctuations are thought to arise from quantum fluctuations during inflation, which were stretched to cosmic scales as space expanded. These tiny variations in density eventually grew under the influence of gravity, seeding the formation of galaxies, stars, and everything else we see in the universe. When scientists looked at the cosmic microwave background radiation, they found exactly these kinds of fluctuations, small variations in temperature that correspond to slight differences in density. The discovery of these fluctuations provided strong evidence in favor of the inflationary model and has helped solidify its place as a central piece of our understanding of the early universe. While cosmic inflation answers many of the questions that the standard Big Bang theory could not, it also raises new ones. One of the biggest mysteries is what caused inflation to start and stop. Gauss's original proposal was that inflation was driven by a hypothetical field called the inflaton field, which had a certain kind of potential energy that caused space to expand rapidly. As the universe inflated, this potential energy would eventually be released, converting into particles and radiation and ending the inflationary period. However, the exact nature of the inflaton field remains unknown. While many theories have been proposed, it's still unclear what the field might be or how it operated. Additionally, some versions of inflation theory suggest that inflation might not have ended everywhere in the universe. Instead, in some regions, inflation could continue indefinitely, leading to the idea of a multiverse, a collection of many universes, each with its own physical properties and laws. Space-time fabric and the birth of dimensions. The origins of our universe are deeply intertwined with the concepts of space and time, two fundamental aspects of reality that seem so intrinsic to our experience that we often take them for granted. Yet, Our understanding of space and time and how they came into existence underwent a profound transformation in the early 20th century, thanks to Albert Einstein's groundbreaking work. His theory of general relativity, published in 1915, revolutionized the way we think about these concepts, revealing that space and time are not merely passive backgrounds against which events occur, but are dynamic entities that play an active role in shaping the universe. Before Einstein, space and time were generally thought of as absolute and unchanging. This view, rooted in the work of Isaac Newton, suggested that space was a vast, unchanging stage where the events of the universe played out, and time was a uniform flow that ticked away steadily, independent of anything else. This classical view worked well for many situations, but it had limitations, especially when dealing with extremely large or small scales or with the gravitational forces found near massive objects like stars or black holes. Einstein's theory of general relativity introduced a radically different perspective. He proposed that space and time are actually part of a single interconnected fabric known as space-time. In this framework, space and time are not separate entities but are interwoven into a four-dimensional continuum where events occur. This space-time fabric is not static. It can be stretched, compressed, and curved by the presence of mass and energy. Essentially, Einstein showed that what we perceive as a force of gravity is actually the result of this curvature of space-time caused by massive objects. One of the most striking implications of Einstein's theory is that the very existence of space and time as we understand them is a result of the Big Bang. In the earliest moments of the universe, when the singularity was still present, the concepts of space and time as we know them may not have existed. As the universe expanded from the singularity during the Big Bang, so too did space and time emerge and begin to take shape. Everything we can see, touch, and measure makes up only about 5%. Despite its abundance, the true nature of dark matter remains one of the biggest mysteries in astrophysics. Scientists have proposed various candidates for dark matter, including weakly interacting massive particles, WIMPs, and actions. But so far, these particles have eluded direct detection. Experiments continue around the world, deep underground, and in space, in the hopes of capturing evidence of dark matter particles, but the mystery remains unsolved. While dark matter exerts a pull on the universe, another, even more mysterious force appears to be pushing it apart. This force is known as dark energy, and its discovery in the late 20th century added a new twist to our understanding of the cosmos. In the 1990s, two independent teams of astronomers, one led by Saul Perlmutter and the other by Adam Rees and Brian Schmidt, were studying distant supernovae, exploding stars that can serve as standard candles to measure cosmic distances. They expected to find that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down due to the gravitational pull of all the matter in the universe. However, their observations revealed something completely unexpected. The universe's expansion was not slowing down but accelerating. This discovery was shocking because it suggested that some unknown force was counteracting gravity and causing the expansion of the universe to speed up. This force was dubbed dark energy, and it quickly became a central focus of cosmological research. Unlike dark matter, which pulls matter together through gravity, dark energy appears to work in the opposite direction, driving the universe apart. The nature of dark energy is even more mysterious than that of dark matter. It is thought to make up about 68% of the universe's total mass energy content, meaning that it dominates the cosmic landscape. One possible explanation for dark energy is the cosmological constant, a concept first introduced by Einstein as a term in his equations of general relativity. Einstein originally included the cosmological constant to allow for a static universe, which was a prevailing belief at the time. However, when it was later discovered that the universe is expanding, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. Ironically, the discovery of the accelerating universe suggests that the cosmological constant might actually describe a real force, dark energy. According to this idea, dark energy is a property of space itself, a kind of energy inherent in the fabric of space-time that drives the accelerated expansion of the universe. However, other theories suggest that dark energy might not be constant at all, but could vary over time, or that it might be the result of some new, as yet undiscovered field or force. The discovery of dark energy has profound implications for the fate of the universe. If the acceleration continues indefinitely, the universe could expand forever, becoming increasingly cold, dark, and empty, as galaxies move farther apart and stars burn out. This scenario is often referred to as a big freeze. Alternatively, if dark energy were to change in strength over time, it could lead to other outcomes, such as a big rip, where the expansion becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atomic structures. Dark matter and dark energy together make up about 95% of the universe, leaving ordinary matter, the stars, planets, and galaxies that we can see and measure, as just a small fraction of the cosmic pie. Yet, despite their dominance, these dark components remain some of the least understood aspects of the universe. They challenge our understanding of the fundamental nature of reality and drive much of the current research in cosmology. How could we detect them or communicate with them? Some scientists argue that the multiverse is an untestable hypothesis, an idea that lies beyond the reach of observation and experimentation, and therefore beyond the scope of science as we currently understand it. However, others believe that the multiverse could leave subtle imprints on our universe that might one day be detectable. For example, collisions between our universe and other bubble universes could leave traces in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the universe. Detecting such imprints would provide evidence that our universe is indeed part of a larger multiverse. Despite the challenges in proving or disproving the multiverse theory, it has become a powerful and influential concept in modern physics and cosmology. It pushes the boundaries of what we consider possible and invites us to imagine a reality that is far more complex and varied than we ever thought possible. The idea of the multiverse also resonates with our deepest questions about existence. Are we alone in the universe? If the multiverse exists, then the answer is both yes and no. We may be alone in our own universe, but we are not alone in the larger multiverse. There could be countless other universes, each with its own version of reality, its own stars and planets, and perhaps even its own intelligent beings, pondering their place in the cosmos. The multiverse theory challenges us to think beyond our own universe and to consider the possibility that the reality we know is just one small part of a much larger, more intricate tapestry. It is a concept that inspires wonder and curiosity, reminding us that the universe, or multiverse, is a vast and mysterious place, full of possibilities that we are only beginning to explore. Time's arrow, the flow from nothing to now. One aspect of our existence stands out as both fundamental and elusive: time. Time is woven into the fabric of our daily lives, guiding the rhythm of our existence, from the ticking of a clock to the aging of our bodies. Yet, despite its omnipresence, time remains one of the most profound and puzzling concepts in both science and philosophy. Perhaps the most intriguing feature of time is its apparent unidirectional flow, a concept famously referred to as time's arrow by the British astrophysicist Arthur Eddington in the 1920s. The idea of time's arrow captures the observation that time seems to move in one direction only, forward. We experience the past as something fixed and unchangeable, the present as the fleeting moment we live in, and the future as something that has yet to unfold. This progression from past to future is something we take for granted, but it raises deep questions about the nature of time itself. Why does time move forward and not backward? Is this flow of time an intrinsic feature of the universe, or is it a product of the way we perceive reality? Arthur Eddington introduced the concept of time's arrow to describe this directional quality of time. He noted that, while the fundamental laws of physics, such as those governing motion and forces, do not inherently favor one direction of time over another, our experience of time is decidedly asymmetrical. For example, when we observe events like a glass falling off a table and shattering on the floor, we intuitively understand that the sequence of events happens in one direction. The reverse, a shattered glass reassembling itself and leaping back onto the table, violates our sense of reality, even though the laws of physics, in their most basic forms, do not explicitly prohibit it. To understand why time's arrow points in one direction, we must consider the concept of entropy, a measure of disorder or randomness in a system. Entropy is a central idea in the second law of thermodynamics, which states that, in a closed system, the total entropy can never decrease over time. In other words, the natural progression of any isolated system is toward greater disorder. This tendency for entropy to increase gives time its arrow, providing a directionality that aligns with our everyday experiences. Imagine a simple example: a cup of hot coffee left on a table. Over time, the heat from the coffee will disperse into the surrounding air, causing the coffee to cool down. This process increases the entropy of the system as the energy, once concentrated in the hot coffee, spreads out and becomes more evenly distributed. We never see the reverse process occur spontaneously, a cup of coffee that cools down and then suddenly heats back up on its own, because this would imply a decrease in entropy, which is statistically improbable. Entropy, therefore, gives us a clue as to why we perceive time as moving forward. The universe, from the moment of the Big Bang, has been evolving from a state of low entropy to higher entropy. The early universe was hot, dense, and relatively uniform, a state of low entropy. As the universe expanded and cooled, it became more structured, with galaxies, stars, and planets forming from the initial chaos. However, as these structures formed, the overall entropy of the universe continued to increase, driven by processes such as the burning of stars and the mixing of gases in galaxies. This increase in entropy over time is what we experience as a forward flow of time. The past represents a state of lower entropy, the present is a point along the trajectory of increasing entropy, and the future holds even greater entropy. The arrow of time, therefore, is not just a feature of our perception, but a fundamental aspect of the universe's evolution. Yet, this understanding of time's arrow raises additional questions. If time is tied to entropy, does this mean that time could theoretically reverse if entropy were to decrease? And what does this imply about the ultimate fate of the universe? Some physicists have speculated that if the universe were to eventually reach a state of maximum entropy, often referred to as heat death, where all energy is evenly distributed and no work can be done, time itself might lose its directionality. In such a state, there would be no observable difference between past, present, and future, because no further change or increase in entropy would be possible. This idea suggests that time's arrow is intrinsically linked to the dynamism of the universe, the constant flux and flow of energy and matter that drives change. The concept of time's arrow also intersects with theories about the origins of the universe. Some cosmologists have proposed that the Big Bang itself represents a kind of temporal boundary, where the arrow of time was set in motion. The universe's most profound mysteries, from the nature of matter and energy to the origins of space and time, the LHC's discoveries have already transformed our understanding of the universe, and its ongoing experiments promise to reveal even more about the fundamental forces and particles that govern reality. In the years to come, the LHC will continue to push the boundaries of what we know, exploring new energy scales and searching for evidence of new physics. It will help answer some of the most profound questions about the universe. What is dark matter? What is the nature of dark energy? Are there extra dimensions of space beyond the three we experience? Is there a deeper underlying theory that unifies all the forces of nature? The answers to these questions could revolutionize our understanding of the cosmos and our place within it. The Large Hadron Collider, by recreating the conditions of the early universe, allows us to peer back in time to the very moments after the Big Bang, when the universe was a seething cauldron of energy and particles. It connects us to the origins of everything we see around us, from the smallest particles to the largest galaxies, and reminds us of the deep connections between the forces that shape the universe and the matter that makes up our own bodies. Through the LHC, we are not just studying the universe's past, we are also exploring its future, seeking to understand the forces that will determine its ultimate fate. Whether the universe will continue to expand forever, collapse in a big crunch, or reach some other end state depends on the fundamental properties of the particles and forces that the LHC is helping to unravel. Current frontos, probing the cosmic dawn. The quest to understand the universe's first moments, often referred to as the cosmic dawn, is one of the most compelling and challenging pursuits in modern science. These early moments hold the keys to many of the mysteries that continue to puzzle cosmologists and physicists today. A range of cutting-edge experiments and observations are providing unprecedented insights into the conditions that prevailed in the universe's infancy. These efforts are pushing the boundaries of our knowledge, revealing the processes that shaped the cosmos from its birth to its current form. One of the most significant milestones in this quest came with the launch of the Planck satellite by the European Space Agency in 2009. Planck was designed to study the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang that fills the universe. The CMB is like a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for atoms to form, allowing light to travel freely through space for the first time. This ancient light carries with it a wealth of information about the early universe's conditions, including its temperature, density, and composition. The Planck satellite was equipped with highly sensitive instruments that measured the CMB's temperature fluctuations with unprecedented precision. Over the course of its mission, Planck mapped the CMB across the entire sky, providing the most detailed image of the early universe ever obtained. These measurements, released in a series of data releases culminating in 2013, refine our understanding of the universe's age, composition, and geometry. One of Planck's most important findings was a confirmation of the universe's age at approximately 13.8 billion years. This measurement, derived from the detailed study of the CMB's temperature fluctuations, matched closely with previous estimates, but with greater precision. Planck also provided insights into the amount of ordinary matter, and dark energy in the universe, revealing that dark energy makes up about 68% of the universe's total energy content, dark matter about 27%, and ordinary matter just under 5%. In addition to refining these fundamental cosmological parameters, Planck's observations offered support for the theory of cosmic inflation, the rapid expansion of the universe in the first fraction of a second after the Big Bang. The tiny fluctuations in temperature observed by Planck are thought to be the imprints of quantum fluctuations in the very early universe, which were stretched to cosmic scales during inflation. These fluctuations eventually led to the formation of galaxies and large-scale structures, making Planck's data crucial for understanding the seeds of cosmic structure. While Planck provided a comprehensive view of the early universe, other experiments have focused on probing specific phenomena that occurred in those first moments. One such groundbreaking effort is the Event Horizon Telescope (EHT) project, which in 2019 captured the first-ever image of a black hole. Although black holes themselves are remnants of stars and not directly connected to the very earliest moments of the universe, the study of black holes offers profound insights into the nature of space, time, and gravity, fundamental aspects of the cosmos that are deeply linked to its origins. The EHT is a global collaboration that links together radio telescopes around the world to create a virtual Earth-sized telescope. This technique, known as Very Long Baseline Interferometry (VLBI), allows the EHT to achieve the resolution necessary to observe objects as small as the event horizon of a black hole, the boundary beyond which nothing can escape its gravitational pull. The black hole that the EHT image is located at the center of the galaxy M87, about 55 million light-years from Earth. This supermassive black hole, with a mass several billion times that of the Sun, presented a perfect target for the EHT's observations. The image, released in April 2019, shows a bright ring of light surrounding a dark shadow, the silhouette of the event horizon. This image provided the first direct visual evidence of the existence of black holes, confirming predictions made by Einstein's theory of general relativity over a century ago. The significance of the EHT's achievement extends beyond the image itself. By studying the environment around the event horizon, scientists can test the predictions of general relativity in the most extreme conditions imaginable. The data gathered by the EHT can help answer fundamental questions about the nature of black holes, including how they grow, how they affect their surroundings, and what happens to matter and information that falls into them. These questions are intimately connected to the study of the early universe, as black holes are thought to play a key role in the formation and evolution of galaxies. Another frontier in the study of the cosmic dawn is the search for the first stars and galaxies, which formed hundreds of millions of years after the Big Bang. These objects, often referred to as population 3 stars, are believed to be the first sources of light in the universe, composed almost entirely of hydrogen and helium, the elements forged in the Big Bang. Detecting these early stars and understanding their formation is crucial for piecing together the history of the universe's evolution from a dark, featureless expanse to the rich and varied cosmos we see today. The James Webb Space Telescope, JWST, set to launch in 2021, represents the next step in this quest. JWST is designed to observe the universe in infrared light, allowing it to peer through clouds of dust and gas that obscure the view of visible light telescopes. With its powerful instruments, JWST will be able to detect the faint light from the first stars and galaxies, providing a direct look at the universe's formative years. JWST's observations will help scientists study how the first galaxies formed and evolved, how they interacted with their surroundings, and how they influenced the subsequent formation of stars and galaxies. This research will build on the foundations laid by the Hubble Space Telescope, which has already provided glimpses of galaxies that existed when the universe was less than 1 billion years old. JWST, with its greater sensitivity and resolution, will push these observations even further back in time, offering an unprecedented view of the universe's earliest epochs. The study of the cosmic dawn also involves understanding the process of reionization, which occurred several hundred million years after the Big Bang. During this period, the universe transitioned from being opaque to transparent, as the first stars and galaxies emitted radiation that ionized the surrounding hydrogen gas. Reionization is a key phase in the universe's history, marking the end of the so-called Dark Ages and the beginning of the universe as we know it today. Experiments such as the Hydrogen Epoch of Reionization Array, HERO, are focused on detecting the faint signals of neutral hydrogen from this period. By mapping the distribution of hydrogen in the early universe, HERO aims to provide a detailed picture of how reionization occurred, how the first luminous objects influenced their surroundings, and how the large-scale structure of the universe began to take shape. At the same time, advancements in gravitational wave astronomy are opening new windows into the universe's first moments. The detection of gravitational waves by the LIGO and Virgo observatories has already revolutionized our understanding of cosmic events such as black hole mergers and neutron star collisions. In the coming years, next-generation detectors, such as LISA, the Laser Interferometer Space Antenna, are expected to detect gravitational waves from even earlier in the universe's history, including signals from the Big Bang itself. These gravitational waves, often referred to as primordial gravitational waves, would provide a direct probe of the universe's first moments, offering insights into the process of cosmic inflation and the conditions that prevailed during the universe's birth. Detecting these signals would be a monumental achievement, allowing scientists to explore the universe's origins in ways that were previously unimaginable. As we continue to probe the cosmic dawn, the collaboration between observational astronomy, experimental physics, and theoretical modeling becomes ever more critical. The discoveries made by experiments like Planck, the EHT, JWST, and HERO are complemented by advances in computer simulations and theoretical work, which help to interpret the data and develop new models of the early universe. These efforts are driven by a fundamental desire to understand where we come from and how the universe came to be. By studying the first moments of the universe, we gain not only a deeper understanding of the cosmos, but also a greater appreciation for the interconnectedness of all things. The search for the origins of the universe is not just a scientific endeavor. It is a deeply human quest to understand our place in the vast and mysterious cosmos.